So up to this point, we have been talking about mostly reactions going in just one direction, right? We feel comfortable thinking about reactants on this side, and then it always proceeds here to products, and then we were done. Now we're going to introduce this concept of a reversible reaction, because most reactions, including those in our bodies, which we're going to cover later in the course, those biochemical reactions, oftentimes those are actually reversible. What this means is that once your reactants have converted into products, your products can then react with each other to go back and make the reactants. This is why we use this double-headed arrow here, or two arrows. Sometimes you'll see this a little different, but the point here is that you're going to have one arrow going in to the right and the other one going to the left. And this is just communicating that this is a reversible reaction. So not only can reactants go to products, but then products can go back into reactants. Oftentimes we'll talk about this as the reaction proceeding to the right or the reaction proceeding to the left. Again, this is just the right is the products, the left is the reactants. So for the rest of the semester, including when we talk about acids and bases in the next lesson and organic chemistry, we will be mostly dealing with reversible reactions. All right, so now what do we mean by equilibrium? So when you have a reversible reaction, think about what you're doing when you're first reacting two species together, for example. So let's say you're in the lab and you have a beaker and you add carbon monoxide and you add water. Initially, these two are going to react and they're going to start forming products. Right? During that time, some of your products will go back and make some reactants. But how these reactions work is that they will make products at some rate, and then the products will make some reactants at another rate. And eventually, as you allow the reaction to proceed, the rate at which reactants are turned to products and the rate in which products are turned to reactants ends up being the same. Initially, those rates are not, but eventually they reach the same rate. And this is what we mean by a reaction reaching equilibrium. So what this looks like from an outside observer is that because those rates are the same, you don't see a net change in concentrations, meaning you don't see any more product being made and you don't see any reactant being made. The concentrations are constant. However, if you zoom in and you look at what the molecules are doing, there is still product being turned into reactant and there's still reactant being turned into product. Nothing is static. Things keep moving. Things keep reacting. It's just that from the outside, it looks like nothing is changing because the net concentrations are the same. And the reason the net concentrations are the same at equilibrium is because the rates in the forward and the reverse reaction are the same. So this is what we mean when a system reaches equilibrium. So now, once your system is at equilibrium, you can disturb this system. There are three different ways in which we can disturb it. We can do concentration, temperature, and pressure. Here, we're only going to look at concentration. The reason we're going to just focus on this one is because this is the one that is going to be most relevant in living organisms, which is what we'll talk about in the last part of this course. Okay, so we're going to look at disturbances of concentration. So what Le Chatelier's principle states is that a system that is at equilibrium is going to react to this disturbance in a way that counteracts this disturbance. Okay, it'll counteract it. So what does that mean? Let's look at an example. All right, so here is a reaction. I have carbon monoxide and oxygen gas reacting to produce carbon dioxide. All right, let's say I react these two and I allow my system to reach equilibrium. Now, once it's at equilibrium, let's say I decide to add more carbon monoxide. What is going to happen to my reaction? Well, if I add more carbon monoxide, I now have excess carbon monoxide that can react to make product in order to reestablish that equilibrium. Because when I added that carbon monoxide, I changed the concentration of my reactant. So I'm no longer at equilibrium. So what this means is that when I add carbon monoxide, I have excess of that. And so that means it will be able to react to make more product until it reestablishes that equilibrium again. So when I introduce that, what's happening at the molecular level to each species in my reaction is that I've added carbon monoxide, therefore it is now going to react with O2. So it will effectively decrease the concentration of O2 in order to make more product. Okay, so it increases CO2. So we refer to this type of reaction as it proceeding to the right. So the adding carbon monoxide will drive the reaction to the right, meaning adding more carbon monoxide is going to produce more product. Let's look at another disturbance. So here I'm still disturbing concentration. That's all we're going to be dealing with. But now I'm going to add more product. Rather than adding more reactant, now I'm adding more product. Well, I've disturbed my equilibrium. So now my system is going to react in a way to restore that equilibrium. So the issue here is that I have too much product because I've added more. So that means that my reaction is going to proceed to the left in order to make more reactant to reestablish that equilibrium. So at the molecular level, what's happening is that I will be making more O2 and I will be making more CO. Both of those concentrations will increase, but they will increase until the equilibrium is established again. That K constant is a constant, so it will not change with these disturbances. Right, let's do an example. In which direction will the reaction proceed given the following changes in concentration? So the first thing I'm going to do is increase H2. So H2 is right here, and I'm going to increase it. Well, that means that my reaction is going to proceed to the right, because now I have too many reactants. So it will proceed to the right until that equilibrium is reestablished. So it goes to the right, meaning it's going to produce product. Right. What if now I increase HCl? So now we're looking at increasing. So again, you're starting at equilibrium, but now you're going to disturb that equilibrium by increasing HCl. Well, now that I have excess product, that product is going to want to turn into reactant to reestablish that equilibrium. So that means that my reaction will have to proceed to the left, and that's going to produce more product. Produce more reactant. Okay, what if we decrease Cl2? Well, for Cl2, if I decrease Cl2, so it's this one here, now I am removing Cl2. That means that now my equilibrium is missing some Cl2. So what the system is going to do is it's going to turn more product into reactant in order to reestablish or reproduce that Cl2 that is now missing. And it'll do that until it reaches equilibrium again. So if I decrease reactant, I remove reactant, then that means my reaction is going to proceed to the left. It's going to produce more reactant because I am missing reactant. So it will try to replenish that. Now, what if I decrease HCl? Well, it's the same idea. If I decrease HCl, that means I'm now missing product at equilibrium. So my reaction is going to proceed to the right in order to replenish that HCl that I have removed. So this is going to be to the right. And what that means is that it's going to produce product.